This video is the beginning of a long series of videos covering discrete mathematics. This is going to follow course material in Math 55 that's covered at Harvey Mudd College. The course covers three bulk topics: number theory, combinatorics, and graph theory, and it's introductory material in all three of these areas. We're going to start with the number theory section, working our way toward RSA cryptography. RSA cryptography is this really cool algorithm that's used in subroutines for encrypting emails throughout the internet. And building up all of the number theoretic foundations that we're going to through the next several videos, we're going to be building up all the way until seeing all of the mathematical underpinnings of the RSA algorithm. So this first section on number theory is going to follow a book that I actually wrote about number theory towards RSA cryptography. So if you want to follow along, feel free to get the book, but you don't have to. You can just watch the videos. So the first video on this topic is going to deal with divisibility and the Euclidean algorithm. And it's going to be motivated by the question, how do you find the greatest common divisor or greatest common factor of two numbers that are relatively large? You could try to do something like prime factorizing if you have familiarity with that as a way of finding the greatest common factor of two numbers. But in general, for very large numbers, prime factorizing is a costly algorithm. So is there a way to do this a little bit differently? That's the motivation of today. So we're going to talk about divisibility and how to get an algorithm for computing greatest common divisors in a way that avoids prime factorization altogether. So stay tuned to this video to find out how to do this. Hey, welcome to today's video. I'm Prof. Omar. This channel is dedicated to undergraduate theorems and problems for your journey through the undergraduate and to prepare for your journey beyond. If this resonates with you, definitely subscribe to the channel and click the bell for notifications. And if you're already a subscriber, thanks so much for coming back. So today we're going to start our journey through the course material in Math 55, which is discrete mathematics at Harvey Mudd College. Starting with the numbers theory section of the course, which is the first third of the course roughly, talking about divisibility and the Euclidean algorithm. So the motivation is to find an algorithm to compute greatest common divisors of numbers in a way that avoids prime factorization so that it's algorithmically not taxing. In order to do this, we need to talk about the underpinnings of divisibility in general. So we're going to take some time to talk about divisibility and properties of divisibility before we talk about the actual greatest common divisor. So let's start with the fundamental definition of what divisibility ought to mean. So given two integers d and a, we say d is a divisor of a if d divides a, meaning there's an integer that we can multiply d2 to get a. So there's an integer k so that a is k times d. Okay, and usually the notation that we use for this, and this is a notation we're going to use throughout the number theory section of this course, is this right here, saying d divides a. This is not a fraction or anything, it's just notation that d divides a. So for example, 3 divides 6 and 5 divides 15. Well, we should be careful and not write things like 6 divides 2, right? I mean, this is not what we're saying, we're writing this in this order right over here. So now that we have this, let's prove a theorem that's going to help us when we're working toward an algorithm for computing greatest common divisors that avoids prime factorization altogether. Say we have three integers d, a, and b, and we're given the information that d divides both a and b. So d is a common divisor of a and b. So the interesting proposition that we're going to prove, which will be helpful for us throughout today and in later videos, is that no matter what integers x and y you select, d has to divide the following combination of a and b. Take a and multiply by x and add b multiplied by y, regardless of what x and y are. So let's give a proof of this, but before we do, let's talk about why something like this might be helpful. So imagine you knew that, or you're searching for a greatest common divisor of numbers like 18 and 12. So you're looking for some number that divides both 18 and 12 and trying to find a number that's as big as possible that does so. Now, whatever this number is going to have to divide any integer combination of x and y. So I use this term integer combination. I should say what it is. This thing right over here is usually referred to as an integer combination. So write that as integer combination of a and b. For those of you who have some experience with linear algebra, of course that's not needed for this video or future videos whatsoever, this can be thought of as sort of inheriting the terms from linear algebra the terms being a linear combination. So a linear combination of A and B, if they were vectors, would be like a scalar multiple of A plus a scalar multiple of B. So we're using that term here, integer combination. If you don't know that, linear algebra stuff doesn't matter. You can think about this as just literally a combination of two integer multiples of A and B. Okay, so if D is a common divisor of these two numbers, it has to divide this combination. And so the strategy here is, if you pick these sort of cleverly, like if you pick x to be 1 and y to be -1, this actually implies that D divides a number that's smaller than both 18 and 12. And that kind of maneuver is going to be really advantageous in the algorithm that we develop, starting with two large numbers and finding a number that's smaller that this D would have to divide. Okay, so let's go ahead then and actually give a concrete proof of this statement. I'll usually write something like PF as the notation for proof. Okay, so we're given the following information. D divides A. So because of that, we know there is an integer, that A is an integer multiple of D. So there is an integer K, so that A is K times D. Now in a similar light, because B is a multiple of D is a divisor of B, we have another integer, say K prime, so that B is K prime times D. Okay, now if we put all of this together with this expression, we can say that AX plus BY is KDX plus K prime DY. And here we can factor out D and get KX plus K prime Y. It doesn't really matter what this expression is. The point is that this expression now is a multiple of D, right? So this gives us the conclusion that we want, that D actually does divide the quantity AX plus BY. Okay, so a cool consequence here, and it kind of feels intuitive. If A is a multiple of D, then AX is, because it's a multiple of A, has to be a multiple of D as well. And so BY is a multiple of D by the same kind of argument, and the sum of two multiples of D is a multiple of D. That's essentially what we're using here. But again, the advantage of having this, and the reason for going over this argument, is that when we start with A and B, we can maneuver around to get smaller numbers that D must divide if it divides both A and B. Okay, so now that we have this in our arsenal, let's go ahead and actually make a concrete definition of what a greatest common divisor is, and then start to work towards developing an algorithm for actually computing the greatest common divisor. All right, so what is a greatest common divisor? From the wording, it is a common divisor that's the greatest among all common divisors. So this is going to play a role in how we actually make our definition. If A and B are positive integers, the greatest common divisor of A and B is the positive integer D satisfying two properties. So this is our number D, and it's going to satisfy that it's a common divisor, so D divides both A and B. I'm going to write this here in parentheses as the common part. But then it's also the greatest common divisor. So if you give me any other common divisor, D has to be greater than or equal to that number, because D is the greatest. So if C divides A and C divides B, then C is less than or equal to D. Okay, so let's look at an actual example of seeing how to develop the greatest common divisor of two numbers using this idea. So let's look at the greatest common divisor of the two numbers 18 and 12. All right, so we kind of played around with this a little bit earlier, and I'm going to write here this proposition that we used, that if D divides two numbers, then it divides any integer combination. I'll just write it in shorthand form. Okay, so if we're looking for the GCD of these two things, let's call it D. Then we know D divides 18 and D divides 12. Okay, and then by that, using this, D divides 18 times 1 plus 12 times -1. And that means that D divides 6. Okay, so if D is a common divisor is the greatest common divisor of these two, then D has to divide 6. But notice this property right over here actually is true just by assuming that D is a common divisor, not the greatest common one. So by this argument, if we pick any common divisor of 18 and 12, that common divisor has to divide 6. But 6 is actually a common divisor of both 18 and 12. So if any divisor has to divide 6, and 6 is a common divisor, then 6 is the biggest one. And so 6 is the greatest common divisor of 18 and 12. So this is a really cool argument that completely evades any kind of factoring of the numbers 18 and 12 using the definition together with this linear combination observation that we made earlier. So this is going to become helpful when we try to compute the greatest common divisor of two numbers that are a lot larger. So we're going to see exactly how that works just in a little bit. Okay, so to motivate how to find the greatest common divisors of two numbers that are much larger than just 18 and 12, I want to think about a way to sort of start with the greatest common divisor of these two large numbers that we're working with and reduce the problem to the greatest common divisor of two things that are smaller. And the idea is to start with your larger number and divide by the smaller one. If you do that, then you get a quotient and a remainder. So the quotient is going to be, in this case, 1369, and this is actually twice that, plus a remainder, which works out to 185. Okay, so take this number, divide by this, you get 185. All right, so what does this tell us? Well, if you think about a number, like this number here, that divides both 2923 and 1369, then it definitely divides 1369, and it also has to divide 185. So the reason is because if we rearrange this and write it instead as 2923 times 1 plus 1369 times negative 2 equals 185, then because D divides both this and this, D divides any integer combination of these two, and this number here, the remainder upon division, is an integer combination of these two starting numbers. So that means that this D actually divides 185. So D is a common divisor of 1369 and 185. And the idea we're going to employ is actually the fact that this GCD of these two numbers can be replaced by the GCD of these two numbers. So not only is this D that we randomly selected a divisor of both 1369 and 185, it's actually the greatest common divisor. So why is something like that helpful? We'll give a proof of the fact that this works in a minute. So the idea is, well, we reduce this problem to the GCD of two numbers that are smaller, but we can play the game again. We can take 1369 and divide it by 185. Right? In this case, if we do that, we'll actually get 7 copies of 185 and a remainder of 74. So the GCD of these two, by the same argument we used over here, where we replaced this pair by this pair, is going to be the same as the GCD of this pair replaced by the GCD of this pair. And you see, these numbers are much smaller to work with than the numbers that we started with. If we do this again, taking 185 and dividing by 74, we'll get 2 times 74 plus 34, or 37. Okay, so then, by the same argument again, the GCD of these two will be the GCD of 74 and 37. And this is much more manageable to compute. 74 happens to be twice 37, so the GCD of these two is actually 37. But by this cascading effect, the GCD of these two is the GCD of these two, which is the GCD of these two, which is then the GCD of these two. So this GCD actually is 37. So it's kind of a really cool way to compute GCDs, and it works because of the equality of the GCD of these two and these two at every step when we do the division and then collect a remainder. So we should actually prove that this process of taking a number, dividing by another, getting a remainder, and doing the GCD replacement actually works. So that's going to be the contents of the next thing that we prove. So what we want to prove is that if we take a number, divide by another number, get a quotient and a remainder, that the GCD of the two original numbers, A and B, is the same as the GCD of the two remaining numbers, B and R. So let A and B be positive integers and Q and R be such that when we take A, we divide by B, we get the quotient and a remainder. The remainder then has to be between 0 and B minus 1. Then the GCD of AB is the same as the GCD of B and R. Okay, so the way to think about this process is the argument we made just previously is that if you have two numbers, a number that divides both A and B, then it has to divide both B and R. Any common divisor of A and B is a common divisor of B and R. So you can think about making two lists, right? So I'm going to call this a proof sketch because I'm not going to write out all the details. You can think about making two lists. So divisors of A and B. So maybe I'll say common divisors, actually. So we have common divisors of A and B. And then another list, which is common divisors of B and R. Okay. So here you have a list of numbers, and here you have a list of numbers. And I think the point here is that if D is a number in this list, right, then that means that D divides A and divides B. And if we move this QB over, that means D divides A times 1 plus B times negative Q. That's an integer combination of A and B, so that means D divides R. So if D divides A and B, then D divides B, and because it already did, and D divides R. And so D is a common divisor of both B and R. So anything in this list is in this list as well. But by a similar argument, if we pick something over here, it divides both B and R, so it has to divide this integer combination of B and R, Q times B plus R times 1, which means it divides A. It already divided B in the first place, so it divides both A and B. And so the list that we have here of all common divisors of A and B is the same as the list of all common divisors of B and R. So if you look at these two lists, this is like the list of all the common divisors of this pair and all the common divisors of this pair, then the lists look the same. So the greatest element in each list has to be the same number. And the greatest element in this list is the greatest common divisor of these two. The greatest element in this list is the greatest common divisor of these two. So the greatest common divisors are actually the same. Okay, cool. There is one point to be made here, though. We have to argue that you can even do this division process in the first place. This is something that we take for granted from our experiences, that if you take two whole numbers, oh, I should mention here that we should have assumed A is greater than B. That's an important point. You can't do this division if you had a number A that's smaller than B. You won't get the right thing. So A being greater than B, then you can actually find a quotient and a remainder that is small, meaning it's less than B. That's essential to our algorithm. The statement that you can actually do this, even though we usually take it for granted, is called the division algorithm. And a proof is given actually in the number theory book that I mentioned earlier in this video. So I'm not going to give a proof in this video, but the proof is there. Okay, so now that we have this at our arsenal, we can replace the GCD of a pair with a pair that looks objectively smaller. Let's look at the consequences at actually developing an algorithm for determining the greatest common divisor of a pair of numbers. So going back to our motivating example, which was the GCD of 29, 23, and 1369, here is the process and how it plays out using what we just proved before. So we take 29, 23, divide by 1369, and get a quotient and a remainder. Then we use those two smaller numbers, repeat the process, repeat again, repeat again. All right, so if we do that, we get that the GCD of this pair is the same as the GCD of this pair. And then this pair cascades here to give us the GCD of this pair and this pair are the same. And that's this pair and this pair right here, etc. And we eventually end with the 0 remainder at the bottom. And the number that seems to be the GCD is this number right over here. Because we have a 0 here, this number is a multiple of this thing. And so the greatest common divisor of these two is actually the smaller number right over here. Okay, so here's the process illustrated with these two numbers, and we got the GCD nicely without doing prime factorizing. And you can see that this would have been complicated otherwise, because if this is the greatest common divisor, then 37 is a weird prime factor. The other prime factors might be weird as well. So really cool process. A few observations. You notice that the numbers are getting cut down quite quickly. Like you start with 29, 23, and whatever remainder you end up with is going to be more than half as small. So you're really knocking down these numbers really rapidly. Okay, so there's two things we need to do to actually establish that this number right here, when you go through this process, actually is the greatest common divisor. We need to check why it is, and it's sort of illustrated by this repeated process, right, where the GCD of these two is the GCD of these two, etc. But one thing we do need to be careful of is to check that this algorithm for general numbers actually does terminate. Right? If we throw in random numbers A and B, we need to know that if we keep going through this process, that this algorithm that we developed actually does end. It doesn't go on forever. And the observation for that is going to have to do with comparing these remainders right over here. So what I'm going to do is erase this example and look at how the algorithm looks in general for general numbers, and then analyze what's happening with the actual algorithm overall in a discussion. And the details of that is actually written up in the book. So I'll go ahead and do that now. Okay, so the general algorithm looks like this, and it's called the Euclidean algorithm. You're given two positive integers. I'm going to label them R1 and R2 because that'll be easier in the indexing to be consistent with what we have here. So say R1 is greater than R2, and our idea is to start with R1, use the division algorithm to divide by R2 and get a remainder. And that remainder has to be between 0 and R2, strictly less than R2. It's in general greater than or equal to 0, but I'm going to demand that it's greater than 0 because I'm going to say we haven't stopped at this step. When we do stop, we'll get a 0 as a remainder, and that's our notice to stop the algorithm. Right? So you keep doing this process until you get a 0 remainder, and then you end. Right? So we did that in the first step and didn't get a 0 remainder, so we continue. Notice the R2 is over here. We divide by the R3 that we had before, and we keep going until we eventually get a 0 remainder. And the argument here is that the greatest common divisor of these two is actually Rn. Okay, so what's the argument behind this? So again, the detailed argument is given in the book, but I'm going to give you a sketch here. So by what we did before, by this division, we get that the GCD of R1 and R2 has to equal the GCD of R2 and R3. Okay, but then by this, we have the GCD of R2 and R3 is the same as R3 and R4, etc. So as we keep going down, all these GCDs are equal. So the GCD of R1 and R2 is going to, at the end, be the same as the GCD of Rn minus 1 and Rn, right? But Rn minus 1 is a multiple of Rn, so their greatest common factor is Rn itself. And so this is indeed the GCD of these two numbers. Now, that verifies that this algorithm outputs the right thing. The thing to check is that the algorithm actually terminates. Well, you start off with R2 being a positive number, and you notice the remainders are a cascading sequence of integers, starting with the positive integer R2, and they descend. You have R2, then you have R3 afterward, then R4 afterward, etc. So you start with a positive integer, and you have a sequence of non-negative integers that decrease. So eventually, you're going to have to get to 0. Right? For example, if your first remainder was 17, then you have to eventually, because you're decreasing, your numbers are decreasing, non-negative integers eventually have to reach 0. And you never go below 0 because all the remainders are always between 0 and the previous remainder by the division algorithm. Okay, cool. So this is an algorithm that is foolproof, works to find the greatest common divisor of two positive integers, and completely avoids prime factorization. We have a general reason why it works. So let's look at least at one example to get a sense of how this plays out and what kind of things you can do with it. So there's this famous sequence in mathematics called the Fibonacci sequence, and it works like this. You start with the number 1, then the next number in the sequence is 1. Then any number after that is the sum of the previous two numbers before it. So 1 plus 1 is 2. So this is a 2 here. The next number is 2 plus 1, which is 3. Then this is 2 plus 3, which is 5. 3 plus 5, 8. 5 plus 8, 13, etc. So I want to look at two consecutive Fibonacci numbers and compute their greatest common divisor. Let's look at 13 and 21. Okay, so according to our division or our Euclidean algorithm, we need to take this and divide by 13. Okay, but we actually know what the consequence of this is going to be. Because 8 plus 13 was 21, this remainder is going to be 8. Now, our process is to take these numbers and apply this again. We get 13 is 8 plus, and then we know that when we divide by 8, we're going to get 5 as a remainder. And if we keep doing this, we start with 8, we divide by 5, we're going to get 3 as a remainder. And then we start with 5, divide 3, we're going to get 2 as a remainder. And then 3, divide 2, we're going to get 1 as a remainder. And then finally 2, we divide by 1, we get 2 copies of 1, and then a 0. So according to our algorithm, this number here should be the greatest common divisor. So the greatest common divisor of these two things is 1. Okay, but notice, inside of all of this, we actually have the Euclidean algorithm for all other subsequent pairs. For example, if we started and asked what the greatest common divisor of 13 and 8 was, we'd have to start with this line and continue downward. So the greatest common divisor of 13 and 8 is 1 as well. Right? And this works actually for any two consecutive ones of these. And so in general, if you look at the Fibonacci sequence and look at two consecutive numbers in it, the greatest common divisor between them has to be 1. And that comes as a consequence of this Euclidean algorithm. It's kind of a neat consequence. And there's a problem in the book that actually asks for how many steps the Euclidean algorithm takes. And it turns out the worst case scenario is the Fibonacci sequence. And the problem talks about how to guide you to get there. Okay, so great. Now we have this cool algorithm for computing the greatest common divisor for two numbers that completely evades using prime factors at all. And we're going to use that throughout the next several videos in order to develop our road toward the mathematics behind the RSA cryptography algorithm. So I hope you enjoyed today's video. If you did, click the like button, and if you want to see more videos like this, definitely subscribe to the channel and click the bell for notifications on future videos.